Solid objects can vanish right before our eyes, leaving only a ghostly whisper behind. This is not a magic trick, but the startling reality of quantum physics, where the very idea of nothing is turned completely upside down. By the end of our journey, you will see the universe not as a collection of static objects, but as a dynamic sea of potential where presence and absence dance in a constant, mysterious rhythm. We will venture into the quantum vacuum, a void far from empty, and uncover how black holes can evaporate into nothingness. What does it truly mean for something to be real when the ground beneath our feet is a whirlwind of fleeting particles and forces? How stable do you believe the world around you truly is? The idea that solid ground might be an illusion is a shock to our senses, yet this notion has haunted human thought for millennia. Ancient Greek philosopher Democritus gazed at the world and saw not solid forms, but a dance of indivisible particles he called atoms, swirling in an infinite, silent void. For him, the empty space between things was not just a passive backdrop, it was a fundamental requirement for motion and change to even be possible. Yet his own student, Aristotle, would push back fiercely. Aristotle's universe was a plenum, a cosmic platter so full that nature itself abhorred a vacuum. He argued that empty space was a logical impossibility, a concept that would unravel the orderly cosmos he envisioned. This intellectual battle between being and non-being set the stage for a scientific quest that would span centuries. The challenge was no longer just philosophical, it became profoundly physical. How could one prove the existence of nothing? In the 17th century, an Italian mathematician named Evangelista Torricelli devised an elegant experiment. He filled a long glass tube with mercury and inverted it into a basin. The mercury did not fully drain, leaving a mysterious empty space at the sealed top. Torricelli had seemingly created a vacuum, a void above the mercury column, but was it truly empty? The brilliant French polymath Blaise Pascal took the inquiry further. He had a version of the experiment carried up a mountain, reasoning that if the column of mercury was held up by the weight of the air, it should drop as the air pressure decreased with altitude. It did. This was a monumental victory for science, yet it came with a haunting revelation. Even in their manufactured void, something elusive remained. A residual presence, a whisper of something that was not mere air, defied total emptiness. These pioneers proved that a perfect nothing was always just out of reach, a ghost in the machine of reality. They were grappling with the edges of a mystery that quantum physics would later plunge into headfirst, showing that the true nature of the void is far stranger and more vibrant than mere emptiness. So this elusive whisper that haunted Torricelli and Pascal finally found its name, the quantum vacuum. But do not let the word vacuum fool you. This is not an empty, silent void. It is the lowest energy state a field can have, the absolute ground floor of reality. Yet this basement is far from dark and still. It is a seething, dynamic arena, buzzing with a kind of transient activity that defies our everyday experience. This bizarre behavior is governed by a fundamental rule of the quantum world, the Heisenberg uncertainty principle. This principle tells us that for incredibly brief moments, energy can be borrowed from nowhere, allowing pairs of particles to spontaneously spark into existence. We call these virtual particles, and they are not like the stable electrons or protons you might picture. They are fleeting ghosts, a particle and its antiparticle partner, appearing together from the empty stage only to annihilate each other an instant later, returning the borrowed energy to the cosmos. This is not a rare event. It is a continuous, frantic dance of creation and destruction happening everywhere, all the time, even in the space between the atoms of the screen you are looking at right now. This zero-point energy field is the new baseline for our universe. It is a vibrant sea of potentiality, and we have proof. Place two incredibly smooth, neutral metal plates extremely close together in a vacuum. In the narrow gap between them, only certain wavelengths of this quantum activity can fit. The activity outside the plates, however, remains unrestrained. This difference in pressure pushes the plates together in a measurable, irresistible force known as the Casimir effect. It is the quantum vacuum itself, this sea of potential, physically nudging objects. So the quantum vacuum is not nothing. It is the fundamental stage upon which all other particles and forces perform their drama. It challenges everything we thought we knew about emptiness, revealing a substance to the void itself. Werner Heisenberg's principle introduced a fundamental fuzziness into the heart of reality. It tells us we cannot precisely know both where a particle is and where it is going at the same time. This is not a limitation of our instruments, but a basic feature of the universe itself. This inherent uncertainty has a breathtaking side effect. For vanishingly brief moments, the strict cosmic ledger that says energy cannot be created or destroyed can be temporarily bypassed. Energy can be borrowed from nowhere, and it must be paid back almost instantly. This fleeting loan is what allows virtual particles to spark into existence. Think of it as the universe's most frantic and precise dance. A particle and its antiparticle twin appear together from the seeming void, exist for a time so short it is almost impossible to conceive, and then rush back together, annihilating one another and returning the energy they borrowed. This is not a theoretical fantasy. We see the footprints of these ghostly dancers everywhere. They subtly shift the energy levels of atoms in ways we can measure with exquisite precision. They are the reason an electron has a faint, additional magnetism that classic physics could never explain. This ceaseless activity means the vacuum is not a still and silent void. It is a bubbling cauldron where something is constantly, briefly, coming from nothing. This forces a profound reconsideration of what we call empty space. If the void itself is this vibrant and active, how permanent is the matter we see around us? The ghostly push of nothingness became an undeniable physical fact in 1948. A Dutch physicist named Hendrik Casimir performed a calculation so elegant it seemed to pull a force from thin air. He envisioned two perfectly smooth, uncharged metal plates placed almost unimaginably close together within a perfect vacuum. In our everyday world, nothing should happen, but Casimir's math revealed they would be drawn together by a faint, irresistible pull. The secret lies in what the plates do to the quantum vacuum. Remember that seething sea of virtual particles, the frantic dance of creation and annihilation. In the wide open space outside the plates, every possible wavelength of this quantum activity can flourish. But in the narrow gap between the plates, only certain wavelengths can fit, like how only specific musical notes resonate in a tiny room. This restriction means there is simply less quantum jostling between the plates than there is on their outer surfaces. With more activity pushing from the outside than from the inside, the plates are squeezed together. This is the Casimir effect. It is not a theory. It has been measured repeatedly in laboratories with stunning precision. Think about that for a moment. We can take two neutral objects, place them in what we would call empty space, and watch an invisible force from the void itself move them. This is the quantum vacuum ceasing to be a philosophical idea and becoming a tangible actor on the physical stage. It is the energy of nothingness, no longer a ghost in the machine, but a real pressure we can see and measure. This profound discovery forces a radical question. If the vacuum is this active, what other spectacular phenomena could it be secretly driving? That same restless energy, the very churn of the quantum vacuum, may have been the spark that ignited the entire cosmos. The most profound implication of this seething nothingness is its potential role in the origin of everything we see. The prevailing theory of cosmic inflation suggests our universe began not with a bang, but with a shudder. A microscopic patch of space-time, no larger than a billionth of a proton, was suddenly gripped by a repulsive force of unimaginable power. This was not an explosion into pre-existing space, but a hyper-fast stretching of space-time itself, doubling its size over and over again in a fraction of a second. What could have triggered such a cataclysmic event? The leading candidate is a quantum fluctuation. In that primordial nothingness, a random, tiny variation in a fundamental field borrowed an immense amount of energy. But this time, the conditions were just right. Instead of the particle pair instantly annihilating as virtual particles do, this fluctuation was caught and frozen by a unique field, its energy unable to be paid back. This single, stabilized blip was then inflated, stretched, and cooled into the entire observable universe. Every galaxy, every star, every planet, and us may all be the descendants of a random microscopic event in the quantum void. Our vast and majestic cosmos could be the ultimate example of something from nothing, a single note plucked from the silent vacuum and amplified into a grand, cosmic symphony. This forever links the fate of everything we know to the unpredictable, vibrant churn of the quantum realm. If our entire universe is the result of one fluctuation that refused to fade, what does that say about the nature of reality itself? This vibrant, energetic void holds the key to the ultimate cosmic vanishing act. Stephen Hawking peered into the abyss of a black hole and saw not a perfect trap, but a leaky one. He dared to merge the rules of the very small quantum mechanics with Einstein's theory of gravity, general relativity, and the result was a prediction that shook physics to its core. Black holes, those legendary cosmic vacuums from which nothing can escape, are not entirely black. Their terrifying grip is undermined by the restless quantum vacuum right at the edge of their influence, the event horizon. Remember those virtual particle pairs flickering in and out of existence everywhere. Normally, they annihilate each other instantly, but at the precipice of a black hole, a gravitational tug of war can tear them apart. One particle of the pair might fall across the event horizon, forever lost to the singularity, while its partner is ejected outward, freed into the universe as real radiation. This is Hawking radiation. To an outside observer, it appears the black hole itself is glowing, emitting a faint heat, but this process comes at a steep cost. The energy for the escaped particle has to come from somewhere, and it is siphoned directly from the black hole's immense gravitational energy, causing it to lose mass. An isolated black hole is therefore on a slow, inevitable diet, gradually evaporating over timescales so vast they dwarf the current age of our universe. Yet the implication is staggering. A celestial object once thought to be the most permanent and indestructible thing in existence is, in fact, slowly fading away. It is the most dramatic disappearance imaginable, a mountain of matter dissolving over eons into a faint whisper of warmth. Hawking's revelation forged an unbreakable link between the force of gravity, the rules of the quantum world, and the laws of thermodynamics. It showed that even the most voracious cosmic entities are not immune to the subtle, persistent churn of quantum nothingness. If a black hole can vanish, what in this universe is truly permanent? This slow evaporation of a black hole creates a cosmic crisis that challenges the very laws of physics. The problem is known as the information paradox, and it asks a deeply unsettling question. When the black hole has completely faded away, leaving behind only a faint, featureless thermal glow, what happened to all the information about the things that fell in? Imagine throwing a detailed encyclopedia, a complex sculpture, and a family photograph into a fire. The fire burns everything to ash and heat, but in principle, a being with perfect knowledge of physics could reverse the process, analyzing the smoke and ashes to reconstruct every page of the book, every curve of the sculpture, every smile in the photo. Quantum mechanics insists that this fundamental information about a system is never truly destroyed, only transformed. It is a sacred rule of the universe. But a black hole that evaporates seems to be the ultimate shredder. It consumes a star with a unique history and intricate structure, and it supposedly emits only random, generic heat. If that information is truly lost forever, it would mean that the universe has a fundamental forgetting, a cosmic amnesia that breaks the most trusted rules we have for how reality operates. This paradox forces physicists to confront an impossible choice. Either our understanding of quantum mechanics is wrong, or our picture of black holes is incomplete. Most scientists believe the answer lies in the Hawking radiation itself. Perhaps the information is not lost. Maybe it is imprinted onto the escaping radiation in an incredibly subtle, scrambled code, like a message hidden in the static of a radio signal. Decoding that message, however, is currently beyond our comprehension. The information paradox is not just a technical puzzle, it is a glaring signpost pointing toward a deeper truth. Our two most powerful descriptions of reality, general relativity and quantum mechanics, are at war over the fate of information in the void. Resolving their conflict requires a new theory, a framework of quantum gravity that can finally explain what truly happens when matter faces the ultimate nothingness. The ultimate disappearance happens in a flash of pure energy. When a particle of matter meets its perfect mirror image, a particle of antimatter, they vanish together in an instant. An electron and its opposite, a positron, do not simply fade away. They mutually annihilate, converting every bit of their substance into a burst of intense light, gamma-ray photons. This is the ultimate demonstration of Einstein's most famous equation, E equals mc squared. Mass and energy are two sides of the same coin, and this process is the cosmic mint, transforming solid substance into radiant, massless energy. It is not destruction, but a perfect, instantaneous transformation. This is not a rare event confined to science fiction. In laboratories around the world, physicists use powerful particle accelerators to create and study this very process, watching matter disappear before their instruments. But its most profound role was played out in the first moments of our universe. In that primordial inferno, matter and antimatter were created in nearly equal amounts, destined to meet and annihilate in a storm of light. Yet a tiny 1 in a billion asymmetry allowed a sliver of matter to remain. From that fragile remnant, from that single page saved from a cosmic bonfire, every galaxy, star, and planet was forged. This means our entire material existence is a testament to a disappearance that was not an end, but a beginning. The most energetic vanishing act in the cosmos was, paradoxically, the very creative force that cleared the stage for everything we know. This probabilistic magic extends even to the very heart of our Sun. Deep within its core, protons, each carrying a positive charge, desperately need to get close enough to fuse and release the energy that makes stars shine. But there is a formidable wall in their way, the electrostatic repulsion that pushes identical charges apart. Classically, the protons in the Sun do not individually possess enough energy to smash through this barrier. They should simply bounce off each other forever. Yet the Sun shines. It shines because of quantum tunneling. Each proton, behaving as a wave of probability, has a tiny but real chance of simply appearing on the other side of that energy wall, as if a section of the barrier simply was not there for an instant. This is not a forceful breach, it is a ghostly transit. The sun is not a mighty furnace overpowering nature's laws, but a cosmic casino where the odds, while incredibly small, are played trillions upon trillions of times every second. Our very existence hinges on this relentless, invisible vanishing act occurring at the heart of every star. This principle is not confined to distant suns. It is harnessed in devices here on Earth, like the scanning tunneling microscope. This remarkable instrument uses a needle with a tip so fine it ends in a single atom. It is brought excruciatingly close to a surface without touching it. Electrons then tunnel through the empty space between the tip and the sample, creating a tiny electrical current. By tracking how this current changes as the needle moves, the microscope can map the contours of a material with such precision that it can render individual atoms visible. We are literally using the ability of particles to be where they should not be to see the building blocks of our world. Quantum tunneling reveals a universe where the impossible is merely improbable. It tells us that a particle is not just a tiny ball in a specific location, but a cloud of potential, a set of probabilities with a faint but ever-present chance of defying every expectation. The line between a solid wall and an open door becomes, at the quantum level, nothing more than a question of odds. This constant dance of creation and destruction finds its deepest explanation not in particles, but in something far more fundamental. The universe is not built from a collection of tiny, solid balls. Instead, every particle is a momentary excitation, a tiny knot of energy in an invisible, omnipresent entity known as a quantum field. Think of the universe as a vast, still ocean. This ocean is not made of water, but of countless overlapping fields, one for each type of particle. The electron field is everywhere. The quark field is everywhere. The electromagnetic field stretches across all of reality. In its calmest state, this cosmic ocean is what we call the vacuum. It is not empty, it is simply quiet. Now, imagine tossing a single pebble into this still water. The ripple that spreads out is not the water itself, but a disturbance moving through it. In exactly the same way, an electron is simply a localized ripple, a tiny vibration in the universal electron field. A photon is a ripple traveling through the electromagnetic field. What we perceive as a solid particle is just a brief, concentrated hum in this cosmic background. This elegant perspective reframes everything. Particle creation is no longer a magical appearance from nothing. It is the act of adding a packet of energy to a field, causing it to vibrate in a specific location. Annihilation is simply that vibration calming down, the energy being released as the field settles back to its quiet ground state. The frantic activity of the quantum vacuum is just these fields at their absolute minimum energy, still quivering with potential, unable to ever be perfectly still. This is why particle numbers are not conserved. A field can be excited or calmed. A ripple can appear or fade away. It explains why two photons can collide and create an electron and its antimatter partner, a positron. They are just transferring energy from the electromagnetic field to excite the electron field in two specific ways. Matter becomes a temporary manifestation, a fleeting pattern in an eternal, dynamic tapestry of fields. Its disappearance is not an end but a return. The substance fades, but the stage upon which it played remains vibrant and full of potential, waiting for the next ripple to begin. So the tangible world begins to feel like a magnificent illusion. quantum physics does not just rewrite our science books, it shatters the very foundations of what we consider real. For centuries, Western philosophy has largely operated on a simple binary, a clear distinction between what exists and what does not. An object is either there, solid and present, or it is absent. But the quantum vacuum, buzzing with virtual particles and spontaneous energy, dissolves this clean line. What does it mean to be if the ground state of reality is a sea of transient potential? The chair you are sitting on feels solid, yet it is a whirlwind of quantum fields whose constituent particles are, at their heart, temporary excitations, here one moment and gone the next. This is not just impermanence, it is a fundamental blurring of being and non-being. The universe seems to operate on a spectrum of existence, where a virtual particle on the verge of reality is not quite nothing, but not quite something in the way we understand it either. This profound shift echoes ancient wisdom from various traditions. Buddhist philosophy, for instance, has long taught the concept of emptiness, not as a void of nihilism, but as a state of interdependent origination where nothing possesses a permanent, independent self. Everything is in a state of flux, a continuous process of becoming. The stable, separate objects we perceive are, in this light, a convenient illusion projected by our senses onto a far more fluid and interconnected reality. The quantum realm seems to be whispering the same truth in the language of mathematics. It challenges a purely materialist view that reality is composed of little, solid building blocks. Instead, it suggests that relationships and potentialities are more fundamental than the things themselves. This forces a reconsideration of our own place in this cosmic dance. If the particles that constitute your body are fleeting patterns in an eternal field, what does that say about the self? Are you a static entity or a constantly refreshing process, a stable flame fed by the transient fuel of quantum activity? The mystery of nothingness thus becomes a deeply personal inquiry. It invites us to see the cosmos not as a collection of isolated things, but as a unified, dynamic whole where presence emerges from a fertile ground of absence. The void is not an end, but a beginning, the silent source from which all possible symphonies of existence can be played. These fleeting quantum ripples are captured and made real within the world's most powerful microscopes. Deep beneath the border of France and Switzerland, the Large Hadron Collider runs a 27-kilometer ring, a cathedral of science dedicated to a single, profound purpose. It smashes beams of protons together at velocities approaching the speed of light. In the heart of its massive detectors, two specks of matter, smaller than any grain of sand, are hurled toward a head-on collision. For a single, blinding instant, their immense kinetic energy is concentrated into a point smaller than a proton. In that flash, the original particles are utterly destroyed. But from that energetic fireball, new forms of matter burst into existence. The tracks of these newborn particles spiral through powerful magnetic fields, captured by layers of sophisticated electronics. Some of these entities are so unstable they survive for less than a billionth of a second, barely long enough to travel the width of an atom before they decay, transforming into a shower of lighter, more familiar particles. This is not magic. It is the direct, observable conversion of pure energy into matter, a dramatic confirmation of Einstein's enduring equation. The collider is not creating something from nothing, but it is revealing the fluid nature of substance itself. It takes the latent potential of the quantum fields and gives it a massive, concentrated jolt of energy, forcing that field to vibrate in new, temporary patterns we recognize as massive, short-lived particles. Every collision is a miniature recreation of the universe's most energetic moments, allowing us to study the properties of particles that flicker in and out of reality so quickly they can barely be said to have existed at all. This violent, controlled process provides undeniable proof that matter is not a permanent state, but a temporary configuration of energy, a borrowed shape that the quantum vacuum is always eager to reclaim. This relentless observation can literally freeze a system in time, a strange quantum phenomenon named for the ancient Greek philosopher Zeno takes his paradoxes about motion to an unbelievable extreme. Zeno famously argued that a flying arrow must be motionless at every single instant of its flight, and therefore true motion is an illusion. The quantum Zeno effect brings a startling, literal truth to this ancient puzzle. It states that an unstable quantum system can be prevented from changing, from decaying or shifting to another state, if we watch it intently and continuously. The mechanism lies in the strange nature of wave function collapse. Every time we measure a quantum system, we force it to pick a definite state, resetting its internal clock. If these measurements come in a rapid, relentless barrage, the system simply does not have time to evolve. It becomes trapped, frozen in its initial condition by the very act of being observed. This is not just a thought experiment. Researchers have demonstrated it by repeatedly measuring the spin of atoms. When left alone, the atoms would quickly flip. But under the constant glare of measurement, they remained locked in place. This forces us to confront a profound question. What is the role of the observer in shaping the fabric of reality itself? It implies that under the right conditions, unwavering attention can impose a strange, artificial stability, halting the natural processes of change and decay that we take for granted. The quantum world seems to suggest that to see something is not just to witness it, but to interact with it in a way that can alter its destiny. If watching closely enough can make a potential reality disappear, what does that say about the world we choose not to look at? The apparent stability of our universe might be the most delicate illusion of all. This concept, known as vacuum decay, presents a scenario where the very nothingness we have explored could turn against the fabric of everything. Our cosmos may not be resting in its most comfortable, lowest energy state. Instead, it could be perched in a false vacuum, a precarious valley of stability that is not the true bottom of the cosmic landscape. Think of a ball resting in a small dip on the side of a vast hill. It seems stable, but a sufficiently strong nudge could send it rolling down into the much deeper valley below, a state of truly lower energy. In our universe, that nudge could be a single, random quantum fluctuation in the vacuum itself. A tiny bubble of true vacuum could then spontaneously form. This bubble would not be empty space as we know it. Inside it, the fundamental constants and the laws of physics would be entirely different. The properties that allow for atoms, molecules, and life would be rewritten in an instant. This bubble would then expand in all directions at the speed of light. There would be no warning, no sound, no flash of light. One moment, reality as we know it exists. The next, an expanding wall of new physics would sweep through the cosmos, not destroying matter in an explosion, but transforming it into something utterly unrecognizable, effectively causing everything we know to vanish from existence as we define it. From our perspective, it would be the ultimate, instantaneous disappearance. The cosmic stage itself would be rebuilt with a new set of rules, potentially one where the drama of stars, planets, and life can no longer be performed. While the probability of this happening in any given year is astronomically small, perhaps lower than any number we can easily conceive, the hypothesis itself serves as a profound reminder of the latent potential within the void. It suggests that the quantum vacuum is not a passive backdrop, but an active participant whose deepest nature could still hold surprises that rewrite the entire story of reality. This accelerating expansion is not just a distant curiosity, it is a fundamental rewrite of our cosmic destiny. For decades, astronomers believed the universe's growth was slowing after the Big Bang, destined to coast to a gradual halt. Then, observations of distant supernova delivered a stunning revelation. The cosmos is not just expanding, it is speeding up, as if some unseen force is pushing all the galaxies apart. This mysterious driver was named dark energy, and its nature is the greatest puzzle in all of cosmology. One compelling explanation points us right back to the quantum vacuum, to the very nothingness we have been exploring. If the vacuum energy, the baseline hum of all those quantum fields, possesses a positive value, then according to Einstein's theory of gravity, it should generate a gravitational repulsion. It would act as a kind of anti-gravity, stretching the very fabric of space-time itself. This would make the quantum vacuum the engine of cosmic acceleration, the silent force behind the universe's runaway growth. Yet here we encounter a problem of almost incomprehensible scale. When theorists calculate the expected energy density of the quantum vacuum based on the known particles and fields, the number they get is staggeringly large. But when astronomers measure the actual strength of dark energy driving the acceleration, the value is almost zero. The difference between these two numbers is not a small factor. It is a discrepancy of over 120 orders of magnitude. To grasp that scale, imagine a single grain of sand. Now imagine that grain of sand compared to the entire observable universe. The difference in size between that grain and the cosmos is only about 40 orders of magnitude. The vacuum energy problem is vastly larger. A miscalculation so profound it is like predicting a tidal wave and observing instead the faintest ripple in a pond. This is the cosmological constant problem, and it represents a catastrophic failure of our two most successful theories to agree on the value of nothing. It suggests that either our understanding of quantum field theory is deeply flawed in some unknown way, or there is a miraculous, perfect cancellation happening, a fine-tuning so exact it seems to defy random chance. This immense puzzle directly tethers the ultimate fate of the cosmos, whether it will expand forever into a cold, dark emptiness or eventually reverse course, to the enigmatic properties of the quantum void. The answer to why the universe is accelerating may not lie in some exotic new substance, but in learning what nothing itself truly weighs. This web of invisible connections stretches across the entire cosmos. Two particles born from the same quantum event can be flung to opposite sides of the galaxy, yet they remain mysteriously linked. This is quantum entanglement, a bond so profound that measuring one particle instantly determines the state of its distant partner. Einstein called it spooky action at a distance, a phrase that perfectly captures the deep unease this phenomenon provokes. It defies the classical rule that nothing, not even information, can travel faster than light. There is no signal, no beam of energy passing between them. The connection is immediate and silent, as if the universe itself does not acknowledge the space between them as a barrier. This is not about matter disappearing, but about the very definition of a thing. An entangled particle does not have its own definite properties until it is measured. Its spin, its polarization, its very identity exists only as a set of possibilities, a shared secret with its partner. The moment you observe one, you force its twin, no matter how far away, to snap into a corresponding state. It challenges our most basic intuition about separateness. How can two objects be distinct if what happens to one defines the other, instantly and irrevocably? This spooky action hints at a deeper layer of reality, one where the universe is not a collection of isolated points, but a single, woven tapestry. The apparent independence of objects in space might be a grand illusion. Their properties are not confined to a specific location. but are instead distributed across a holistic network of relationships. When you measure one part of this web, the entire pattern shifts in response. This suggests that if a particle seems to vanish, its essential information might not be lost at all. It could simply be transferred or preserved within this vast, interconnected whole. The disappearance of a localized property is not an erasure, but a refocusing of the cosmic pattern. The universe at its heart may operate as an unbroken unity, where every part remembers its connection to the whole. A quantum particle, when left entirely alone, is not in one place or another. It exists as a shimmering cloud of probability, a mathematical entity called the wave function that holds every possible future for that particle within it. This is the state of superposition where an electron can be spinning both up and down at the same time, or a photon can be taking every conceivable path through an experiment simultaneously. It is a world of pure, unmanifested potential, yet the moment we look, the moment we set up a detector to ask it a simple question, that ethereal cloud vanishes. The wave function collapses and we find a single, definite answer. The particle is here, not there. Its spin is up, not down. The infinite potential has crystallized into one concrete reality. This abrupt transition is the measurement problem, and it asks a question that cuts to the core of our understanding. What is so special about measurement? Why does the mere act of observation cause this dramatic shift from a world of and to a world of awe? The equations of quantum mechanics describe this collapse, but they do not explain what physically triggers it or where the line is drawn between the quantum realm and our own. The Copenhagen interpretation, the traditional view, places the observer in a privileged, almost mystical role. It suggests that consciousness itself is the final ingredient that forces possibility to become actuality, that our awareness is the sculptor that carves a single reality from the quantum marble. This view, while influential, leaves many scientists uneasy, as it seems to insert a profound mystery at the very heart of scientific inquiry. An alternative, the many worlds interpretation, offers a breathtakingly different solution. It proposes that the wave function never actually collapses. Instead, at the moment a measurement is made, the universe itself splits. Every single possible outcome predicted by the wave function does, in fact, occur, but each one plays out in a newly branched parallel reality. In one world, you see the electron spin up. In another, an identical version of you sees it spin down. There is no disappearance of possibilities, only a proliferation of entire cosmos, a vast, ever-expanding multiverse where every quantum roll of the dice pays out somewhere. This problem is far more than a philosophical debate. It is the essential bridge between the fuzzy, probabilistic quantum realm and the sharp, definite world we experience every day. It asks how the ghostly dance of potentialities backstage gives rise to the singular, solid performance we see under the lights. The mystery of how possibilities vanish is perhaps the greatest disappearing act in all of nature. The elegant equations of general relativity and the bizarre rules of the quantum world cannot both be the final word. They stand as two magnificent, yet warring, descriptions of reality. One paints gravity as the gentle curvature of a smooth, continuous spacetime, a cosmic fabric molded by mass and energy. The other reveals a microscopic realm of frenetic jumps and ghostly probabilities, where smoothness is an illusion. For decades, physicists have searched for a single theory that can marry these two visions, a framework of quantum gravity that can tell us what happens when the immense force of a black hole meets the fuzzy uncertainty of the quantum. In the leading candidates such as string theory or loop quantum gravity, a radical idea emerges. The very stage of the universe, the space-time continuum itself, may not be fundamental. Instead of a smooth, infinitely divisible backdrop, space and time could be quantized, emerging from something more basic. Picture the surface of a still pond. From a distance, it appears perfectly smooth and continuous, but bring your eye infinitely close, and you would see the frantic dance of individual water molecules. In the same way, if we could peer down to the universe's smallest possible scale, the Planck length, the serene fabric of space-time might dissolve into a seething, discrete foam. In this primordial froth, the concepts of here and now lose their meaning. Tiny wormholes might blink in and out of existence, and the geometry of space itself would be in constant, violent fluctuation. The stage upon which the drama of virtual particles and quantum leaps plays out would itself be alive, a churning ocean of potential geometry. This suggests the mystery of nothingness runs deeper than we ever imagined. It is not just that particles can vanish into the void, but that the very arena of that vanishing, the concepts of location and moment we hold so dear, might themselves be temporary, emergent properties. The quest for quantum gravity is ultimately a search for the true nature of the canvas upon which all of reality and all of its disappearances are painted. This holographic view of reality turns our intuition about space inside out. It suggests that the entire three-dimensional universe we perceive, with its galaxies, stars, and planets, might be a magnificent illusion projected from a distant, two-dimensional surface. The information required to describe every particle, every force, and every event within a volume of space could be entirely encoded on its outer boundary, like a cosmic DVD storing a three-dimensional movie on its flat surface. This is the holographic principle, a revolutionary idea born from the fiery intersection of black hole physics and string theory. Its origins lie in a stunning calculation about black holes. Stephen Hawking showed that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the area of its event horizon, its two-dimensional surface. The amount of information a black hole can contain is limited by the surface area of its boundary, not the volume within it. This was a profound clue that the fundamental degrees of freedom in our universe might be vastly fewer than we imagined. The universe may not be built from tiny pixels of volume, but from tiny tiles of surface area. If this is true, then the solidity of the chair beneath you, the vast emptiness between stars, and even your own conscious experience are all a grand projection. It is as if we are living inside a hologram where the true, raw data of existence is stored on a faraway screen we can never directly see. When a particle and its antiparticle annihilate in a flash of light, or when a black hole evaporates into Hawking radiation, we are not witnessing matter vanishing into true nothingness. We are watching information being recoded, recalculated, and rewritten on that fundamental two-dimensional surface. The disappearance is only an artifact of our limited, three-dimensional perspective. The world we experience is a shadow, a rich and convincing rendering of a deeper, simpler, and perhaps more beautiful information-theoretic reality. This forces us to ask a staggering question. If our vibrant, three-dimensional world is a projection, what or who is the projector? This ghostly push from the void is now being carefully measured in laboratories, not just for curiosity, but for invention. The same Casimir force that draws two plates together in a vacuum is being explored as a potential component for machines on an almost unimaginably small scale. In the realm of nano-electromechanical systems, where components are mere billionths of a meter across, this quantum effect could one day be engineered to create switches and sensors that operate with virtually no friction, eliminating the wear and tear that plagues their larger counterparts. It is a profound inversion, using the persistent pressure of nothingness to build more resilient and efficient something. This practical research into the vacuum's energy also fuels a deeper scientific dream, the study of zero-point energy. While the notion of tapping this sea of energy for limitless power remains firmly in the realm of science fiction, the effort to understand its staggering density pushes our knowledge of thermodynamics and quantum field theory to its absolute limits. The true technological power of the quantum vacuum, however, is already at work all around us. The bizarre rules governing virtual particles are not optional. They are essential for our most precise descriptions of reality. The theory of quantum electrodynamics, or QED, incorporates the frantic dance of particle creation and annihilation into its very core. Without accounting for these fleeting ghosts, its predictions would be subtly, yet undeniably, wrong. The accuracy of QED is so phenomenal it is like predicting the distance between New York and Los Angeles to within the width of a single human hair. This spectacular precision is the hidden foundation for the laser in your DVD player, the magnetic resonance imager in your local hospital, and the very transistors that form the heart of every modern computer. Our deepest understanding of empty space has directly enabled the devices that define our modern world. The abstract mystery of quantum nothingness is no longer confined to the blackboard. It has been coaxed out of the void and encoded into the silicon and steel of human innovation, proving that by staring deeply into the void, we learn not only about the cosmos, but how to reshape our own. This delicate balance of cosmic numbers presents a profound puzzle. The fundamental forces and constants of nature hold values that seem almost miraculously precise. If the strong nuclear force were just a few % stronger, the universe would be a sea of helium with no hydrogen to form water or fuel stars. If it were slightly weaker, complex atomic nuclei could never have coalesced. The mass of the electron, the charge of the proton, even the incredibly tiny value of the vacuum energy we call the cosmological constant, all appear to be set to a razor's edge. A universe with even marginally different numbers would be stillborn, incapable of forging the complex structures that lead to planets and life. This is the enigma of fine-tuning. It feels as though the cosmos was designed with our existence in mind. But is that truly the case? One compelling explanation shifts our perspective from a single universe to a vast multiverse. Imagine a cosmic landscape where countless universes are constantly bubbling into existence, each with its own random set of physical laws and constants. In the overwhelming majority of these universes, the numbers do not add up. Some might collapse instantly back into nothing, while others fly apart too quickly for stars to ever form. But in a rare few, by sheer statistical chance, the constants align perfectly to allow for galaxies, chemistry, and conscious life. We, of course, find ourselves in one of those exceptionally rare habitable patches. This is the anthropic principle in action. It suggests that we observe a universe finely tuned for life, not because it was made for us, but because we are a product of its specific, life-permitting conditions. Our very presence as observers selects for this particular cosmic lottery ticket. This perspective weaves the mystery of the quantum vacuum directly into the story of our own consciousness. The puzzle of why the vacuum energy is so infinitesimally small, a number that seems unnaturally set to zero, might find its answer here. In a multiverse where every possible value of this energy is realized, we inevitably inhabit one of the rare universes where it is small enough for galaxies to coalesce and thinkers to emerge. Our ability to ponder the void is therefore inextricably linked to the specific, quiet nature of the void we call home. The act of observation becomes the final, necessary link in a chain of cosmic accidents. binding our conscious minds to the deepest properties of nothingness itself. Our own minds are the final barrier to understanding this quantum realm. Human brains evolved to dodge predators, find ripe fruit, and navigate a world of solid objects and predictable cause and effect. This classical wiring makes the quantum domain feel alien and deeply unnatural. How do you visualize a single electron being in many places simultaneously before you measure it? How do you picture empty space not as a still void, but as a frenetic sea of transient energy? We are trying to see a 10-dimensional universe with a brain built for 3. To bridge this gap, scientists rely on metaphors. They describe the quantum vacuum as a bubbling foam or a fluctuating energy field, like the surface of a pot of water just before it boils. These images are powerful and helpful, but they are also flawed approximations. The quantum foam is not actually a froth of little bubbles you could see, and a field is not a literal fabric you could touch. They are mathematical concepts that we dress in familiar language because we have no other way to speak about them. This cognitive struggle is not just a problem for the public. Even the physicists who develop these theories admit they cannot truly visualize what the equations describe. They work with the math, trusting its internal logic and its spectacular predictive power, even when it points to a reality that defies every instinct. This forces a humbling realization. The true nature of quantum nothingness might be a reality that exists beyond the limits of visual imagery. It is a landscape best navigated with the abstract tools of mathematics and probability. Our senses, so perfectly tuned for survival on this planet, may simply be the wrong instrument for perceiving the deepest layers of the cosmos. We are left to interpret the shadows on the cave wall, knowing the fire casting them is a form of light our eyes were never built to see. The same mathematical beauty that governs a snowflake's crystal pattern also lies at the heart of the cosmos. Symmetry is a silent architect in physics, a principle demanding that the laws of nature remain unchanged under a transformation, like a perfect sphere looking identical from every angle. In the universe's first, searing moments, this symmetry was absolute. The fundamental forces we know today, electromagnetism and the weak nuclear force, were unified into a single, pristine force. In that hot, energetic state, particles like electrons and quarks were massless, zipping through the cosmos at the speed of light. They were pure energy, indistinguishable in their lack of substance, part of a perfectly symmetric vacuum. But perfection is often unstable. As the universe expanded and cooled, it crossed a critical threshold like water freezing into ice. This was a moment of spontaneous symmetry breaking. The pristine, uniform state became unstable, and the universe had to choose a new, stable ground state, one that was less symmetric. This is where the Higgs field enters the story. Think of a room filled uniformly with a mysterious, invisible mist. In the early hot universe, this Higgs mist was perfectly symmetric, having the same value everywhere. But as things cooled, it was as if this mist suddenly condensed, settling into a specific, non-zero value throughout all of space. This new, stable configuration broke the original symmetry. Now, as particles move through this condensed Higgs field, they interact with it. Some particles, like photons, pass through completely unaffected, remaining massless. Others, like electrons and quarks, get bogged down, wading through the cosmic mist as if it were a kind of quantum resistance. This resistance is what we experience as mass. The particles did not simply gain weight, they acquired a fundamental interaction with the vacuum itself. Their mass is a testament to a broken symmetry, a relic of a more perfect past. So the solidity you feel, the very substance of your body, did not simply appear. It emerged, crystallizing from a more symmetric state as the cosmos transitioned into a new phase of reality. The diverse matter we see today is the direct result of a cosmic cooling, a great settling that turned a featureless, energetic void into a structured world where things could have weight, form, and ultimately existence. So where does all that quantum weirdness go when we look at the world around us? Why does a single electron exist as a shimmering cloud of possibilities, while the chair you are sitting on remains stubbornly and reliably in one place? The bridge between these two realities is a process called quantum decoherence, and it solves one of the deepest mysteries in physics. When a quantum system is perfectly isolated, it can happily exist in a superposition, its multiple potential states coexisting in a delicate harmony. But isolation is a fantasy in our bustling universe. The instant this system interacts with its environment, even by bouncing off a single photon of light or a stray air molecule, something profound happens. The system becomes entangled with its surroundings. Imagine a single, perfectly still bell. If you strike it, it rings with a pure, clear tone. This is like a pristine quantum state. Now imagine that same bell in a room with 1,000 other bells, all connected by invisible threads. When you strike your bell, the vibration travels through all the threads, setting off a chaotic, collective ringing. The pure tone of your original bell is lost, drowned out in the chorus of the environment. This is decoherence, the clean, wave-like interference between the different possibilities in a superposition is destroyed, scrambled by countless interactions. From our perspective, the system is no longer in multiple states at once. It appears to have chosen one definite classical reality. This process is incredibly fast and relentless. For a tiny particle like an electron, it might take a minuscule fraction of a second. For a large object like a chair, constantly bombarded by trillions of air molecules and photons, decoherence is instantaneous. The quantum weirdness does not vanish into nothingness. It leaks out, spreading into the environment in an irretrievably complex way. Decoherence provides the missing link, explaining how the sharp, definite world of our experience emerges from the fuzzy quantum substrate without any magical collapse. The solidity of the macroscopic world is not a fundamental truth, but a practical reality enforced by our inability to isolate anything from the ceaseless whisper of the cosmos. Einstein himself was deeply troubled by the implications of quantum entanglement. He, along with colleagues Boris Podolsky and Nathan Rosen, crafted a brilliant thought experiment now known as the EPR paradox. Their goal was not to prove quantum mechanics wrong, but to argue it was incomplete. They believed the weirdness, the idea that a particle's properties were not real until measured, was absurd. Surely, they reasoned, there must be some hidden information, some local hidden variables that predetermined a particle's state from the moment it was created. This would restore a sensible, classical reality where things have definite properties whether we look at them or not. For decades, this remained a compelling philosophical argument, a clash of worldviews with no way to settle the debate. Then, in the 1960s, physicist John Bell found a chink in the armor. He derived a mathematical theorem, now called Bell's theorem, which created a clear test. It showed that if local hidden variables were real, then certain statistical results from measuring entangled particles would always stay within a specific bound, known as Bell's inequalities. But if quantum mechanics was correct with its spooky action at a distance, these inequalities would be violated. The universe itself was given a multiple-choice test. In the 1980s, a series of exquisite experiments led by Elaine Aspect performed this test. The results were unambiguous. Bell's inequalities were violated, just as quantum mechanics predicted. There were no local hidden variables. The particles were not simply carrying secret instructions. Their connection was real, instantaneous, and non-local. This was not a failure of our knowledge, but a feature of reality itself. The EPR paradox, intended to show quantum theory was incomplete, ended up confirming its most bizarre prediction. The disappearance of definite properties before measurement is not a flaw in our understanding. It is a genuine, fundamental aspect of how the universe is constructed. We are forced to accept that at its deepest level, reality is not a collection of independently existing things, but a web of relationships where objects are defined by their connections to the whole. Our journey into the void has brought us to the edge of known physics, but the map is far from complete. The coming decades will see a new generation of experiments designed to probe the quantum vacuum with unprecedented precision. Scientists are developing even more sensitive instruments to measure the subtle push of the Casimir effect, hoping to detect the influence of different materials and geometries on the quantum foam. In laboratories around the world, researchers are creating analog black holes using flowing water or ultra-cold Bose-Einstein condensates, not to trap light, but to listen for the sonic equivalent of Hawking radiation. The faint thermal whisper they hope to detect could confirm that this strange evaporation is a universal feature of horizons, not just gravitational ones. Meanwhile, plans are already being drawn for next-generation particle colliders, machines that will dwarf the power of today's giants. These colossal instruments will slam particles together with such ferocious energy that they will illuminate the vacuum structure at scales 1,000 times smaller, potentially revealing hidden dimensions or new symmetries. The goal is to shake the void so violently that it reveals secrets it has held since the first instant of time. These technological marvels are all aimed at answering fundamental questions that still gnaw at the foundations of physics. The black hole information paradox remains a glaring wound in our understanding. Does information truly vanish, or is it somehow preserved, scrambled into a code we cannot yet read on the Hawking radiation? The nature of dark energy is an even deeper enigma. Is it truly the weight of the quantum vacuum? And if so, why is its value so absurdly small compared to our calculations? This cosmological constant problem is a silent scream from our equations, telling us that a profound piece of the puzzle is missing. Underlying all of this is the greatest challenge of all, the quest for a theory of quantum gravity. How do we stitch the smooth, geometric fabric of spacetime described by Einstein to the frantic, discrete jumps of the quantum world? The answer will rewrite our concept of reality itself, telling us what space and time truly are at their most fundamental level. This relentless pursuit is more than an academic exercise. Every time humanity has stared deeply into a fundamental mystery, the answers have reverberated through our civilization, giving us new tools and new visions of our place in the cosmos. The drive to understand quantum nothingness could one day yield technologies we can barely envision, from new forms of energy to revolutionary materials. But the greater reward lies in the journey itself. Each layer of the mystery we peel back reveals not a final answer, but a deeper, more beautiful question, inviting us to look further into the heart of the silent void from which we came. This quantum uncertainty is not confined to the laboratory. It echoes through our greatest stories and artworks. The surrealist painter M.C. Escher did not need to know the mathematics of quantum mechanics to feel its unsettling truth. His impossible staircases that fold back on themselves and his waterfalls flowing in endless loops are visual representations of a world where logic breaks down, where up and down, beginning and end, are no longer fixed concepts. He captured the profound disorientation of a reality without a single, stable perspective, mirroring the quantum realm where a particle's path is not a line but a blur of probabilities. In literature, authors like Philip K. Dick took this further, weaving narratives where the very fabric of reality is suspect. His characters grapple with shifting memories and manufactured worlds, asking what is real when our perceptions can be so easily deceived. These are not just entertaining stories, they are thought experiments that play with the same fundamental questions physicists ask. Can we trust our senses? Is the solid world an illusion? By translating abstract quantum concepts into emotional journeys, these artists give us a new language to feel the mystery. A film that bends time or a song that evokes a vast, empty space can communicate the awe and strangeness of the quantum void in a way a textbook equation never could. This cultural resonance reveals a deep, human impulse to find meaning in the mysterious. Our scientific quest to understand nothingness and our artistic drive to express it are two sides of the same coin. Both are attempts to map the uncharted territories of existence, to find beauty and pattern in the silent, vibrant chaos from which everything emerges. This creative dialogue reminds us that the most profound scientific discoveries do not exist in a vacuum. They ripple out, shaping our culture and touching the very core of what it means to be human in a strange and wondrous cosmos. The staggering cost of a machine like the Large Hadron Collider is not just a financial figure, it is a profound statement of human priority. We must ask ourselves why society invests billions in chasing the ghosts of the quantum void. The answer lies not in immediate gadgetry, but in the very nature of fundamental discovery. Every time humanity has chosen to explore a seemingly abstract frontier, from gazing at the stars to probing the atom, the resulting knowledge has rippled through civilization in unpredictable and transformative ways. The understanding of electromagnetism gave us the modern world, from power grids to global communication. Our investigation into the quantum vacuum could one day yield similar revolutions, perhaps in energy, materials, or computation, that we cannot yet even conceive. This potential for long-term, paradigm-shifting benefit is the ethical justification for the immense investment. It is a gamble on the future of human knowledge itself. Alongside this promise, we must handle the knowledge we uncover with great care. The concept of vacuum decay, while having a probability so infinitesimally small it is effectively zero, is a powerful idea. Communicating such speculative risks responsibly is a critical duty for scientists. Presenting them as frightening, imminent threats is a disservice that can breed unnecessary public anxiety and undermine support for the vital work of basic research. The goal is to share the awe and mystery without the alarm, framing these ideas as fascinating thought experiments that illuminate the edges of our understanding, not as forecasts of doom. As we pull back the curtain on the fundamental workings of reality, the knowledge we gain will inevitably grow more potent. The same principles that explain the stability of atoms could, in distant centuries, inform technologies of immense power. This places a profound responsibility on the global scientific community to pursue this knowledge with transparency and international cooperation, ensuring that the insights born from probing nothingness are used to uplift humanity, not to create new divides. Our journey into the quantum realm is more than a technical quest. It is a philosophical one that challenges our place in the cosmos. By choosing to look deeply into the void, we make a statement about the kind of species we aspire to be, one driven by a courageous and thoughtful curiosity about the universe we call home. Our exploration has revealed a cosmos where the stage itself is alive with potential. From the seething quantum vacuum to the slow evaporation of black holes, we have journeyed across a reality where nothing is truly empty and disappearance is merely transformation. The solid ground beneath our feet is a whirlwind of fleeting excitations in eternal fields, and the vast expanse of the universe may be a holographic projection from a distant, two-dimensional surface. These are not just abstract curiosities. They are fundamental truths that dissolve the classical boundaries between something and nothing, challenging our deepest intuitions about permanence and substance. Every star that shines does so because of quantum tunneling, a ghostly transit through impossible barriers. Every atom in our bodies exists only because a cosmic asymmetry saved a remnant of matter from total annihilation in the universe's first moments. The quest to understand the void is, in the end, a quest to understand the origin, nature, and ultimate fate of everything we know and are. It invites us to see the universe not as a collection of static objects, but as a dynamic, interconnected process where presence emerges from a fertile ground of absence. What we call reality is a single, magnificent note sustained from the silent symphony of the quantum realm. We would love to hear which of these mind-bending ideas resonated most with you. Share your thoughts in the comments below and subscribe to join us on our next journey to the frontiers of knowledge.